على آل محمد رسولنا النبي الأمي المبعوث رحمة للعالمين.
But computers, of course, do so much more than numbers and math and all this low-level stuff. We send text messages, write documents, emails, and the like. So how might a computer represent something like the letter A? I claim at the end of the day, your Mac, your PC, your phone just has lots of transistors, lots of switches that it can use in units of 8, in units of bytes. How, though, if it's already using those patterns of zeros and ones apparently to represent numbers from 0 on up, how do you go about representing letters of the alphabet, might you think? Yeah. OK, so we could assign a number to every letter. OK, so let me just conjecture. Well, let's just call A 0 for simplicity, B 1, C 2. And now let me play devil's advocate. OK, how do I now represent 0 or 1 or 2? Well, we've maybe created a problem for ourselves. If we have to steal some numbers to represent letters, we kind of have to pick a lane. But there's a solution to that, too, that we'll see. And it turns out the world is not quite as simple as A being 0. A typically is represented by computers everywhere, phones everywhere, with the number 65, the decimal number 65. Using 8 bits, if we turn some of the zeros to ones, let me just stipulate, you can represent the letter A using 8 bits by turning certain ones on and certain ones off. But we will try not to focus on that binary level too much. So if A is 65, it turns out that B is going to be 66, and C is going to be 67, and so forth. And so where does that get us? Well, it turns out there's a whole system that maps numbers to letters. And here, as I alluded to verbally a moment ago, is the pattern of zeros and ones via which you'd represent 65. And just quick check here, we won't constantly do math. Ones place, that's easy. 2s, 4s, 8, 16, 32. 64's place, so 64 plus 1 gives us 65. So once I do that, how do I get to all of the others? Well, it turns out a bunch of Americans years ago came up with this, ASCII, the American Standard Code for Information Interchange. Now, what does that mean? Well, it's just an acronym describing what really you proposed, a mapping between numbers and letters. Not quite as simple as 0, 1, 2. Starts at 65, 66, 67 for capital letters. But here are most of the letters in use today, at least with this system. So this is just a big chart from online. And you'll see in the middle of this chart here, here's my 65A. Here's my 66B, C. And let's see, 72 is H. 73 is I, and so forth. So there's a mapping, at least for English, between all of these numbers and all of these letters. And if we focus here, those are the beginning of our uppercase alphabet. So suppose then that today, tomorrow, you receive a text message from someone. And underneath the hood, now that you're a computer person, you figure out a way to see what pattern of zeros and ones was sent. In this case, it's wireless as opposed to wired, but it's still some pattern of zeros and ones. And your phone is turning some switches of its own on and off to represent that message from a friend. Suppose that the 3 patterns you received were these 3 bytes from left to right, spelling out a 3-letter word. Well, if we do out the math, 1's place, 2's place, and so forth, I'll spoil it for you. Suppose that you received a text message that doesn't literally say 72, 73, 33, but you received a pattern of 8 plus 8 plus 8, 24 bits that, if you do out the math, represent the decimal number 72, 73, 33. Anyone recall what message you might have received from the green and white chart? Yeah. Hi. But yes, hi is the message. But 72, 73 gives us H and I. What's 33? Any guesses to 33? Yeah, over here. Yeah, so it's an exclamation point. How would you know that? Well, you really do need some kind of cheat sheet, aka ASCII in this case. And if we look elsewhere, let me highlight the left of the chart. You can see that next to 33 in decimal is indeed the exclamation point. So back in the day, a bunch of humans got in a room, decided that, hey, when we start building PCs and later Macs and phones, we all just have to agree on this form of representation of letters of the English alphabet in this case. We just need to agree on this mapping. But somewhat curiously, notice this. It turns out that once you paint yourself into this corner and start using 65 for A, 66 for B, well, how do you represent 65 the number and 66 the number if you want to do math or use Excel or something like that? Does anyone kind of see the solution, perhaps? How do you represent the number 1 in ASCII? Yeah, in the middle? Yeah, so this is getting a little maybe Inception or something, but you could represent numbers with other numbers. And so if you want to represent the number you and I know as 1, like when you type it on your keyboard, turns out the computer stores that as the decimal number 49. If you hit 2 on your keyboard, the computer's not storing 2 per se, it's storing the decimal number 50. Now, thankfully, the paradox kind of stops there. We just have a mapping now of numbers to numbers. But really, at the end of the day, and you're going to learn this when we start writing code in that other language, C, next week, it's just context dependent at the end of the day. Inside of your Mac, PC, and phone, there's just all of these permutations of bits, all of these patterns of zeros and ones. And generally speaking, when you open up a text message that you've received from someone, it's zeros and ones. But obviously, if it's a text message, the whole point of text messages is to send text. And so those patterns of zeros and ones by default will typically be interpreted as letters of the alphabet. So you won't see zeros and ones. You won't see decimal numbers. You'll see the English message that your friend intended. By contrast, if you open up something like Excel, that same pattern of zeros and ones might indeed work out to be 72, 73, 33. You might see cells in your spreadsheet with literally those 3 numbers. Why? Because spreadsheets are all about numbers and number crunching and math in many cases. If by contrast you open up Photoshop and try to look at that same pattern of zeros and ones, it's not going to be 72, 73, 33. It's not going to be zeros and ones. It's not going to be high. It's going to be some color of the rainbow. You're going to use those patterns of zeros and ones, it turns out, too, to represent colors. And indeed, so long as you and I just agree, as humans long have, what these patterns are going to be, all of our systems, many of our systems nowadays are indeed interoperable. But I'm being very biased here. And indeed, the A in ASCII is very American-centric. What do you not see in this chart? If you speak any other language than English, odds are you're not seeing characters you know and love and need every day to type or send messages. Well, there's a huge character set that's not supported here, whether it's accented characters and a lot of Asian alphabets. You have many more symbols than can fit even on this screen here. And so humans kind of painted themselves into a corner early on, or really Americans did. But on a typical keyboard, US English keyboard, yeah, you have A's and B's and C's, uppercase and lowercase. But you also have accented characters here. And nowadays, not sure if this is maybe necessary, but nowadays you have other characters on your keyboard like these. And these are kind of a playful incarnation of what's actually a technical solution to this problem. If I claim for the moment that ASCII historically used 7 bits to represent letters, and let's just round that up to a byte, 8 bits to represent letters, ASCII can represent as many as 255, or really 256 total characters. Why 256? Well, if you have them all 0, that's 0. And the highest number I claimed a moment ago was 255. So that's 256 total possibilities. That's not many letters. It's fine for English, but not a lot of human languages. So what might the intuitive solution be if you want to represent accented characters, Asian characters, emoji, even like these, which are just keys on a keyboard nowadays? What's the intuitive solution if a byte's too few? Yeah. Yeah, so add another digit. Just like we had a 4th volunteer come on up to give us a 4th bit, let's just throw hardware at the problem and use a few more bits. So maybe instead of 1 byte, let's use 2. Or heck, let's use 3 or 4 bytes. Even though it's getting a little expensive, we're going from 8 to 16 to 24 or 32 bits. That's how computers do things these days. And thankfully, we have so much memory inside of our computers and phones, we can certainly spare a few to represent these things. And the solution then to ASCII is what we'll call Unicode. So Unicode is also just a mapping of letters to numbers to letters, but in many different languages. And indeed, the Unicode Consortium is a bunch of people from all different companies and a lot of different companies and countries and cultures whose mission as an organization is to capture digitally all forms of human language in this case, and to ensure that especially smaller demographics of humans speaking lesser known languages are nonetheless represented and preserved digitally using some mapping of these zeros and ones. It turns out, though, if you start using 32 bits, as many as 32 bits to represent characters on a keyboard, that's 4 billion possible permutations of zeros and ones. That's way more than we need for most human languages. So there's a little bit of room in there for some of those more playful things, like those emoji. So for instance, suppose you got a text message with this pattern of zeros and ones. Or if we do out the math, suppose you receive a text message that if you do out the math in decimal is 4,036,991,106. Anyone know what emoji you're looking at? It'd be weird if you do, but What is this? Well, it turns out that as of this past year, this is the most popular emoji to be sent by many measures. Face with tears of joy. So that is the pattern that a bunch of humans in the Unicode Consortium decided would represent this. But you'll notice many of you might have iPhones, some of you might have Android devices too, and sometimes these don't actually look quite the same. This happens to be the current version of Face with Tears of Joy on iOS. On Android, it tends to look a little something more like this. And here's kind of a curiosity. Even though you and I look at these things and they look like images, they're not images. They're characters, at least as we've defined them now in Unicode. And iOS and Android and Windows and Facebook and other companies and apps nowadays really just have different fonts, if you will. So just like fonts with English and other languages can give you different characters with serifs or not, emoji are themselves, yes, drawings that someone made, but they're really just a font. And so that same pattern of zeros and ones might just render slightly differently on someone's phone or another. If you've ever gotten like an icon on your phone that's broken and you've been sent an emoji, but it's like a square or something arbitrary and not sensible, it might just mean that you have not updated to the latest version of iOS or Android, which just updates the font of supported emoji, because those folks at Unicode pretty much every year nowadays are adding more and more emoji to that particular character set. Now, I went down the rabbit hole figuring out the other day just which are the most popular emoji these days. On Twitter specifically this past year, the most popular emoji, by contrast, was loudly crying face. I don't know if that says more about 2021 or about Twitter, but you'll see different trends certainly in how these are used. But even humans themselves didn't necessarily think 2 steps ahead. And now a lot of the emoji are this sort of default yellow color, but there's a lot of emoji that aren't sort of these cartoon characters, but they're meant to represent humans in various professions or gestures or the like. And nowadays too, you've probably noticed on your phone and Macs and PCs, there are different skin tones that you can assign to certain emojis. If it's supported by the company and by Unicode, you can actually like touch and hold on a certain emoji, and then you can choose the appropriate skin tone to represent yourself or someone else, and that then modifies the display. Well, let's just think for a moment here, how did Apple and Google and Microsoft and others go about implementing support for emoji with different skin tones? How could you do this? If you want to represent some smiling emoji, but in 5, in this case, different skin tones, you could come up with what? 5 different patterns that are identical structurally, except for the skin tone used in places in that image. But that's a little inefficient, right? To kind of just do copy, paste, 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 and like change the color in Photoshop, if you will. That's going to use more bits, more information than you might need to. How else, if you now start to think a little bit more like a computer scientist, if at the end of the day all you have are zeros and ones, how else could you implement skin tones, might you think? Yeah. OK, so RGB, we'll come to that in just a moment. That stands for red, green, blue. That's one way. In this case, though, I'm seeking an alternative to just using 5 different patterns of zeros and ones to represent the same emoji, but different skin tones. So not quite RGB. Yeah. OK, so store one copy of the emoji and then store different variants of the color that you want to assign to that emoji. Yeah, so this is actually an example of, do you want to elaborate? OK, so you can use a loop to actually output these things. More on that in a moment. Let me go down this road for just a moment. This would be, in some sense, sort of a better design, if you will. But why? Yeah. OK, so filter, if we think sort of in the Instagram sense, you can sort of change the color of something. And that could be related here, too. Oh, interesting. So maybe it could be just a completely different font. And you have 5 different fonts that are almost identical, except for the various interpretations of skin tone for those same emoji. Let me spoil. I think if we go down this one particular road, the way the Unicode folks decided to do this some years ago were the first byte or bytes that you receive via text or email just represent like the structure of the emoji, the default yellow version thereof. But if it's immediately followed by a certain pattern of bits that these humans standardized to represent each of these different shades of skin tone, then the phone, the Mac, the PC will change that default color, yellow in most cases, to whatever the more apt human tone is. So you just use twice as many bits, but you don't use 5 times as many bits. So what do I mean? You don't have 5 completely distinct patterns per se. For each of these possible variants, you have a representation of just the emoji itself structurally, and then reusable patterns for those 5 skin tones. Unfortunately, that wasn't quite versatile enough for other features that were in the pipeline. And nowadays, too, and there's a double meaning now to representation, emojis had tended to focus on certain professions. And early on, too, were certain professions associated with certain genders and vice versa. And you couldn't necessarily be one gender or another in a certain profession or another. There were these combinatorics that just weren't possible. But nowadays, as you might have seen, you can have couples in love, for instance, that actually look a little more like 3 emojis, but just kind of combined into one. And indeed, this is just one key press on your phone. And you can combine different emoji on the left and on the right with an emoji in the middle. And so it turns out how computers nowadays represent these patterns are one set of bits for the character on the left, one set of bits for a character on the right, one set of bits for whatever emoji you want in the middle, and then you assemble more complicated compositions of emoji by just reusing those same patterns and bits and bits. Emoji doesn't, the Unicode folks don't have to come up with a whole new representation for some very specific incarnation. They can create one for person, for male, for female, for other characters that you might want to display and reuse those same patterns of zeros and ones. And so here you see sort of the imperfection of, or lack of foresight of humans for building a system early on that was entirely American-centric, no characters, emoji, or the like, that's evolved too. And so that's an important detail in computing nowadays. It too is evolving. And the languages you're about to learn in the coming days, those too are evolving as well. And new features are getting added. And even programming languages have version numbers. You might have a different version of an app on your phone. Programming languages too have different versions as well. Questions then thus far on how information is represented using ASCII or Unicode or anything in between. Yeah? Oh, good question. So to recap, why can't you just, let me summarize that as, why can't you similarly use different patterns to change the context of what these patterns of bits represent, whether it's a number or a letter or a graphic? In actuality, that's kind of what's happening underneath the hood. It's not standardized in quite the same way, but starting next week when we transition from Scratch to C, you'll learn about types, data types, where the onus initially is going to be on you, the programmer, to tell the program whether or not this pattern of bits should be interpreted as a number or as a letter or as a color or something else. Nowadays, though, and toward the end of the semester, you'll use languages like Python, where the computer just figures it out for you by context, which makes it even easier and faster to program as well. Other questions on Unicode, ASCII, or the like? All right, well, how about just a few other forms of information? RGB was called out earlier, red, green, blue. How do images get represented in computers? Well, in fact, it's typically an assembly of some amount of red, some amount of green, some amount of blue. But there are other representations. If you're a graphic designer, you might know them. But RGB is still pretty common. What does this mean? This means to represent every dot on your phone or every dot on your TV or your laptop or desktop, there is a number representing how much red that dot should show, a number representing how much green, and a number representing how much blue it should show, red, green, blue, respectively. So for instance, if a dot on your screen, we're using these 3 numbers, these 3 values or bytes, 72, 73, 33, in a text message or email, that would be interpreted as I claimed hi. But in Photoshop or in some graphical program, that same pattern would be interpreted as, let's call it a medium amount of red, a medium amount of green, and a little bit of blue. And why medium and little? Turns out that each of these are bytes. The smallest value you can have in a byte, we said, is 0. The largest value you can have in a byte is 255. So I'm just kind of spitballing here. This is like medium, medium, and a low amount of red, green, blue, specifically. Those 3 colors, like wavelengths of light, are combined in such a way that you would have this dot on the screen, a sort of murky shade of yellow or brown. That is how a computer would store precisely that color. And in fact, we've seen this color. When you type in "faced with tears of joy," generally on your screen it looks like this, typically much smaller. But let's zoom in. Or let's zoom in a little more. What are you starting to see, if you know the term? So pixels, it's getting very pixelated. A pixel is just a dot on the screen. And if you really zoom in on it, you can literally see all of the dots that compose an emoji, in this case on iOS, in the font that Apple's using to represent this particular pattern of zeros and ones. So one of those yellow dots, and there's many of them, all that kind of blend together here, each dot on the screen, I claim, is 3 bytes. How much red, green, blue for this dot? How much red, green, blue for this dot? How much red, green, blue for this dot? And you'll notice, too, that when it gets to be sort of brownish here, the dots really stand out. The 3 values, the 3 bytes, aka 24 bits, are just slightly different. And so underneath the hood, this is why images, photographs that you take, or GIFs that you download get so darn big, potentially, because you have a number representing every dot on the screen. Well, if this, I claim, is indeed how images are typically represented, using pattern of bits that are assigned to some amount of red, green, or blue, how do you get video? What is a video if at the end of the day all we have are zeros and ones? What's a video, perhaps? Yeah. Oh, let's go here. Way in back.
Is it pixels changing what's their values at different moments in time?
Yeah, pixels really changing values over time. And do you want to confirm or deny the hand that went up here? Yeah. Yeah, or equivalently, a sequence of images that over time are changing on the screen. So both of those are valid interpretations. And, you know, just for fun, if you grew up with these sort of picture books, you might remember a little something like this. If we could dim the lights. So that's sort of the old school analog way of how to implement an image, in the sense that that artist wrote out like hundreds of pieces of paper with almost identical images, but where the ink from their pencil or pen was slightly moving. And if you digitize that such that each of those strokes are represented with dots instead, that's really what you're seeing, is a sequence of all of these images flying across the screen. And if we dive into the real world, if you've ever watched a film, a Hollywood movie is typically 24 FPS, frames per second. That really means you're seeing 24 images per second. Or on TV or in soap operas, it's often 30 frames per second. That makes things look a little more smooth. So it's not actual motion picture, if you will. It's sequences of pictures, and your brain and mine are kind of interpolating that, oh, this is smooth movement, even though we're just seeing a lot of pictures really fast. Now, that gets really big, and we'll talk later in the semester how you can compress information so that you're not using way more bits than you actually need to, and there's fancy algorithms that folks have developed. But at the end of the day, that's really all a video might be, is a sequence of images. Conversely, if you want to represent the music that accompanies that or something else, if any of you play an instrument and can read sheet music, how could you digitize this? Like, how could you represent musical notes in a computer? You and I hear them when we play files, but what's really going on underneath the hood? Any musicians? Piano players? Anyone? Yeah. OK, so hertz value, so some frequency. So sound is some frequency, and it's kind of hitting your eardrum, and that's what makes it sound low or high or somewhere in between. So maybe we could assign, just like there's letters A through G here, maybe we could assign specific frequency values, which are just going to be numbers measured in something called hertz, something per second. And maybe we could have a few other numbers for each of these notes, not just the note or the frequency. Maybe we could represent the loudness of it, like how hard or how softly a human might equivalently press it. Maybe a third number, like duration, like how long is their finger on the keyboard. So you could imagine quantizing something like music that in the real world is perfectly continuous as something more discrete by representing each note over time as just some sequence of values. And there's so many different ways to do this. MIDI, if you've heard, MP3s, AAC. I mean, almost all of the file extensions you see on your Mac or PC, if you see them at all, ultimately just mean there's a different form of representation for, in this case, something like sound. So let me just stipulate, there are these and many more ways to represent inputs and outputs. And thankfully, humans have standardized a lot of this. They don't always disagree. And this is why we have different file formats for Apple numbers and Microsoft Excel and Google spreadsheets and sort of stupid incompatibilities like that. But generally speaking, humans have standardized how we represent the inputs and outputs to and from problems.